Many Cold War histories assert that the Soviet Union lost the computer revolution the moment it failed to wire its own territory. Historians often use a specific metric to define this outcome: the inability to build a nationwide data network, frequently labeled the Internet. The contrast is usually framed by this map. While ARPANET successfully connected the United States, the Soviet attempt stalled into an incomplete grid of fragmented, incompatible nodes. This creates a historiographical paradox. It fails to explain how a supposedly broken computing apparatus supported a 700,000-person IT industry and deployed advanced automated management systems across every major defense sector. Equating the socio-political collapse of a specific state networking project with the failure of a nation's foundational computer science is a mistake. Two mathematicians, Anatoly Kitov and Viktor Glushkov, engineered the theoretical framework that defined the Soviet digital era. Their central project, this State Automated Management Information System, or OGAS, suffered a socio-political immune response, which is a different outcome than a failure of technical design. The rapid, transparent flow of digital data physically collided with the rigid, mechanical structure of the Soviet administrative state. The Soviet bureaucratic system identified transparent, automated data systems as a fatal threat to its administrative command power structure. Evaluating the true legacy of Soviet computing requires moving past the rejected national network to examine the successful mathematical and architectural outputs of the Kitov and Glushkov schools. In 1955, Anatoly Kitov published a paper that rescued cybernetics from ideological exile, moving it from the category of pseudoscience into a legitimate field of Soviet study. Kitov's 1959 Red Book project followed, representing the first formal proposal for a nationwide computer network. He proposed the Unified State Network of Computing Centers, or USNCC, as the nation's technical backbone. This diagram shows the USNCC's dual-purpose architecture, with data pathways flowing simultaneously between fortified military command nodes and civilian economic planning centers. The state rejected the project immediately. Kitov was stripped of his position and expelled from the Communist Party. The proposal required a shift toward scientific management, which would have stripped administrative power from mid-level party bureaucrats. This established the permanent tension in Soviet computing, where advanced technical foresight was repeatedly crushed to ensure state self-preservation. Viktor Glushkov advanced the science further in 1961 with his monograph, Synthesis of Digital Automata. Glushkov's breakthrough translated physical computer components directly into abstract algebraic expressions. Engineers could manipulate these mathematical abstractions to optimize system logic before soldering a wire. This allowed algorithms to directly dictate hardware design via Project CAD systems. Glushkov's theorem on the regularization of arbitrary algorithms provided a foundation for structural programming, reaching many of the same conclusions Edsger Dijkstra would later popularize in the West. His work transformed computer engineering from a trial-and-error electronic process into a rigorous mathematical discipline. Managing an entire national economy created a data volume that standard von Neumann computer architectures were unable to process. Glushkov developed a hardware solution for this specific bottleneck, the macro-conveyor architecture. This diagram compares the architectures. On the left is the standard serial bottleneck. On the right is the macro conveyor, an early MIMD architecture where multiple independent units execute distinct commands on separate data streams at the same time. This theory resulted in the construction of the ES2701 and EU1766 computer systems. These machines achieved nominal capacities exceeding 1 billion operations per second. The macro conveyor proves that Soviet hardware design was heavily engineered to scale for the extreme data demands of central planning, regardless of whether the state chose to deploy it. Applied cybernetic systems functioned successfully in the USSR whenever they were isolated from state macro politics. The Lviv management system, deployed at the Electron television plant in 1967, demonstrated that automated enterprise management was entirely feasible. This model was refined into the Kuntsevo system, which became the standard resource planning equivalent across 9 separate defense ministries. While local successes were tolerated, the national rollout of Glushkov's OGAS network was viewed as a threat. The final OGAS design was massive, calling for 100 regional hubs connecting exactly 20,000 local enterprise nodes across the country. The Central Statistical Administration killed the project. While they cited high costs, their primary fear was the loss of political control over economic reporting. OGAS was a victim of political assassination by a bureaucracy terrified of algorithmic transparency. The evidence from the Kitov and Glushkov schools forces a re-examination of the aborted national network. The state macro network failed to connect, but the individual nodes, the mathematical logic, and the enterprise management systems were highly successful in isolation. In 1982, Glushkov published his theoretical culmination, Fundamentals of Paperless Informatics. The text provides a predictive mathematical model for the modern digital economy and the transition into an information society. It detailed the exact digital environment required to replace bureaucratic paper planning with automated matrices and vectors. Dismissing Soviet computing because of a missing ARPANET equivalent misjudges the science behind it. Kitov and Glushkov provided the technical blueprints for a digital future. The Soviet state simply failed to adopt to them. When we tell the story of the Internet, we usually start in the West. In the late 1960s and 70s, researchers built ARPANET, wiring together computers across North America and Western Europe with rapid, glowing network nodes. But look at the map of that same era, and the world's largest country is entirely dark. The Soviet Union, covering a sixth of the Earth's landmass, had no equivalent public network. Because of this gap, there's a common assumption that Soviet computer science simply lagged behind, that they lacked the theoretical chops to build complex digital networks. That assumption ignores the work of two men, Anatoly Kitov and Viktor Glushkov. They were the pioneers of Russian informatics. Decades before the West began talking about the Internet, these scientists engineered comprehensive, highly detailed blueprints to run an entire national economy on a digital backbone. They called their final proposal the State Automated Management Information System, or OGAS. It was designed to link 20,000 interconnected computing nodes in a strict hierarchy. These blueprints were mathematically sound and technically advanced, yet they were never fully realized, raising the question of why a system designed to optimize the state was ultimately seen as a threat to its survival. In the 1950s, at the highest levels of the Cold War, computing was viewed almost exclusively as a military tool. Machines were built to calculate missile trajectories and manage the space race. Anatoly Kitov ran the Soviet military's very first computing centers. His teams handled the complex math required to put early Soviet satellites into orbit. These facilities were physical behemoths. Operating them required interacting with massive analog dials, heavy switchboards, and teams of technicians manually feeding instructions. Kitov realized that the massive processing power used to aim rockets could be redirected. Instead of calculating ballistics, computers could process the production and distribution data of the entire Soviet economy. To make that leap, the hardware needed to evolve. This is where Viktor Glushkov stepped in. He introduced a way to formalize computer hardware design using rigorous mathematics. In his work, Synthesis of Digital Automata, Glushkov demonstrated how complex computer components could be mapped out as exact algebraic expressions. He moved computer engineering away from trial-and-error soldering and turned it into hard, predictable science. Combining Kitov's macroeconomic vision with Glushkov's scientific hardware design provided the necessary components to create a cybernetic state. Running a planned economy requires collecting and sorting millions of daily data points. The immediate engineering hurdle was achieving massive processing speed. In 1959, Kitov led the development of the M100 computer. It reached an operating speed of 100,000 operations per second, making it one of the most powerful machines on the planet at the time. This schematic illustrates CPU instruction pipelining. The M100's architecture allowed data to move efficiently through staggered processing stages, meaning the computer didn't have to wait for one command to finish before starting the next. But even accelerating a single processor wasn't enough to manage a national economy. A different architectural approach was needed to process an entire nation's data. The proposed solution was Glushkov's macro conveyor concept. Instead of pushing data sequentially through one fast pipe, the macro conveyor processed multiple, distinct data streams simultaneously. Today, computer scientists classify this as MIMD, multiple instruction, multiple data processing. This design effectively bypassed the standard von Neumann bottleneck, preventing the system from choking on its own data transfer limits. By solving this hardware bottleneck at the micro level, Soviet engineers proved they had the theoretical computational bandwidth to direct a macro-level economy. A nationwide network can't exist without functional local nodes. Before wiring the country, they had to prove the system could work on a factory floor. In 1967, Glushkov's team deployed the Lviv system at a massive television manufacturing plant. The Lviv system automated core management, tracking inventory levels, managing personnel schedules, and calculating daily output in real time. In modern terms, they had built one of the world's first functional enterprise resource planning, or ERP, systems. Their software was specifically coded for a highly structured, regular stream of tasks. This was a stark contrast to Western universal systems from IBM, which were designed to solve random, varied task flows from multiple different users. Getting the ERP concept working at a single enterprise was the vital operational proof they needed. Now, they were ready to link thousands of these factories together. The plan to connect them was first outlined in 1959. Kitov authored the Red Book project, which proposed a unified state network of computing centers. This was a dual-purpose architecture. Kitov envisioned a hybrid network whose processing tower would be shared by both the military and the civilian economy. The military rejected sharing their hardware, but the idea survived, and in 1962, state leader Alexei Kosygin directed Glushkov to take up the mantle. Glushkov evolved Kitov's initial proposal into the OGAS project. The blueprint established 100 high-capacity regional nodes in major industrial centers. These hubs connected downward to 20,000 local enterprise computing centers. The network operated in one direction, automatically pushing real-time reporting data upward to feed massive macroeconomic planning models at the top. Unlike the horizontal communication model of ARPANET, OGAS operated as a cybernetic nervous system designed to replace administrative guesswork with absolute, centralized data transparency. In 1964, the final OGAS blueprints were presented to the highest levels of Soviet administration in Moscow. The plan immediately hit a wall. The primary resistance came from the Central Statistical Administration and Gosplan, the State Planning Committee. OGAS posed a direct threat to these middle management layers. A network that fed raw factory data straight to an automated macroeconomic model completely bypassed their manual control of economic statistics. The loss of that control, and the political power that came with it, motivated the bureaucracy to block the network's implementation. Under subsequent leadership, officials officially dismissed the project, citing extreme complexity and high financial cost as the reasons for shutting it down. But the unspoken reality was job preservation. State leaders feared being replaced by objective computer models, leading to rumor spreading that a punch card would soon control the Kremlin. A centralized digital network struggles to coexist with an administrative command bureaucracy, which relies on the control of information to maintain authority. While the macroeconomic network died on the vine, the micro-level engineering survived. Kitov and Glushkov systems were compartmentalized. Instead of wiring together a unified public economy, they built siloed, highly secure networks for specific defense ministries. Kitov went on to create the Algem programming language, standardizing associative programming to handle complex economic logic. Glushkov shifted focus to paperless informatics, accurately predicting the digitization of daily administrative life decades before it became a reality. Viktor Glushkov's early theoretical work on algorithmic algebras directly laid the vital mathematical groundwork for what we now call modern structural pattern recognition. Their early theoretical work in digital automata and simulation systems formed the baseline for much of modern global artificial intelligence research. The theoretical architectures engineered by these scientists outlived the empire that rejected them. Their designs prove that the history of computing is defined as much by theoretical breakthroughs as it is by the successful laying of cables. The Western historical consensus holds that the Soviet Union lost the Cold War technology race because they failed to build a nationwide, decentralized computer network. Because this Soviet internet never materialized, often mockingly referred to by historians as the Internet, Western scholars long assumed that Soviet computer science was entirely backward or stagnant. Evaluating Soviet technology through the lens of Western capitalism ignores the specific requirements of the Soviet model. Judging their technology on its failure to build a peer-to-peer web overlooks the highly advanced, centralized cybernetic architecture they were actually attempting to construct. Anatoly Kitov and Viktor Glushkov were the chief architects and visionaries of this alternative IT ecosystem. They operated in a state-run command economy, where horizontal peer-to-peer communication serves no function. Markets did not set prices or manage supply chains. Managing national production quotas requires a network designed for top-down computational execution and strict vertical hierarchy. Kitov and Glushkov engineered massive centralized national network blueprints, specifically projects known as the Red Book and OGAS, to fulfill this exact requirement. While political bureaucracy ultimately strangled the national rollout of these networks, the theoretical computer science required to draft them rivaled and in some cases preceded Western developments. In 1959, Anatoly Kitov submitted the Red Book project, the first formal blueprint for a nationwide cybernetic architecture. At the center of this proposal was the Unified State Network of Computing Centers, or USNCC. This map shows a network topology where specific fortified military defense nodes are directly linked to civilian economic planning centers. Kitov designed a dual-purpose architecture. The processing power required by the military would be shared with civilian administrators to manage the command economy during peacetime. Soviet leadership approved scaling up the production of physical hardware, but they rejected the integrated network concept. The military elite and party leaders were deeply suspicious of administrative transparency. They refused to share computational control with civilian ministries. Kitov's failure highlighted the central paradox of the Soviet IT effort. Technical capability was secondary to preserving political power. Kitov was eventually removed from his position and expelled from the party for his persistence. By the early 1960s, Viktor Glushkov took the conceptual baton from Kitov, shifting the focus to rigorous mathematical foundations. At the time, global computer engineering relied heavily on manual, trial-and-error circuit design and physical testing in the laboratory. Glushkov broke away from this in 1961 with his theoretical monograph, Synthesis of Digital Automata, which introduced the algebraic theory of automata. This theory allowed physical computer hardware to be represented entirely as abstract mathematical equations. Engineers could then use these algebraic expressions as blueprints to automatically generate optimized circuit topologies. This methodology created the foundational logic for modern computer-aided design, or CAD systems. Glushkov's theory shifted Soviet computer development from a localized engineering craft to a mathematically scalable science, enabling the creation of systems with billion operation per second performance. Glushkov recognized that standard physical computing architectures would hit processing speed limits if scaled to manage a national economy. The standard computing model of the era, the von Neumann architecture, processes instructions sequentially, creating a data bottleneck. To bypass this, Glushkov proposed a non-von-Neumann macro-conveyor architecture. In modern systems engineering, this is defined as MIMD, multiple instruction, multiple data. This animated schematic illustrates the MIMD architecture. It allows a system to process multiple unique command streams simultaneously against multiple distinct datasets. The ultimate result was the creation of systems like the ES-2701, which utilized macro conveyors to shatter the 1 billion operations per second barrier. Glushkov's team developed architectures capable of handling the high-volume data streams of a centralized state, moving beyond Western sequential designs. The hardware and mathematical bedrock established by Glushkov culminated in his 1964 proposal. He called it OGAS, the State Automated Management Information System. It was engineered specifically to manage the Soviet macroeconomy in real time. The proposed network blueprint operated on a staggering hierarchical scale. This diagram outlines the topology. A supreme central node at the apex branches to 100 regional hubs, then down to 20,000 localized enterprise nodes. The network relies on strict directional flow. Local data flows strictly upward. Planning commands cascade downward. In sharp contrast to the ARPANET, OGAS featured absolutely zero horizontal peer-to-peer communication between local nodes. OGAS functioned as a technocratic engine intended to replace human bureaucratic chaos with mathematical control. The mathematical perfection of the OGAS blueprint crashed directly into the volatile reality of Soviet mid-level politics. In 1964, the Central Statistical Administration systematically rejected the OGAS project. Cybernetic networks require absolute data transparency. For middle management bureaucrats, this transparency was a threat to their autonomy. Soviet administrators relied on driving the product shaft, a system of quota inflation and data falsification used to secure resources and promotions. OGAS would have eliminated the ability to falsify these quotas, stripping the bureaucratic class of their primary survival mechanism. The Soviet state depended on accurate data for national planning, yet it rejected the very architecture capable of providing it to preserve the power of its administrators. While the nationwide macro network was killed, cybernetic theory was successfully deployed on a microscale. Glushkov pivoted to implementing localized automated management systems in specific enterprises, such as the Lviv television plant and the Kuntsevo radio plant. Dismissing the entirety of Soviet computer science simply because they failed to launch a nationwide web is historically negligent. The technical achievements that did survive, macro-conveyor architectures, algebraic digital automata, and advanced structural programming theories, demonstrate a high level of innovation. Glushkov and Kitov did not fail as scientists. They engineered the theoretical and industrial bedrock for a digital economy that survived long after the system that commissioned it. The standard historical narrative of the Cold War tech race usually concludes that the West built the Internet, while the Soviet Union failed to keep up. We measure this race against the benchmark of ARPANET. It was a decentralized, peer-to-peer mesh designed to route data around damage. When we look at the Soviet Union through this lens, we see a blank map, a failure to network. This narrative relies on a flawed assumption. The Soviets focused on an entirely different set of technical goals. Judging Soviet computer science by its failure to invent the Internet obscures their actual, radically different technological objective. In the 1950s and 60s, scientists like Anatoly Kitov and Viktor Glushkov pioneered a distinctly Soviet computational vision. Their objective was to engineer a macroscopic computational engine capable of running a centralized command economy in real time. This required an entirely different structural approach to computing. Instead of facilitating the flexible exchange of consumer data, their designs prioritized raw industrial calculation and absolute economic control. While their overarching political project eventually stalled, the mathematical and architectural research required to pursue it created world-class computer science, developed completely independent of the West. Mathematically managing a planned economy, tracking every ton of steel, every grain harvest, and every factory quota across 11 time zones demanded extreme computational power. At the time, Western commercial computing focused heavily on basic business tabulations and payrolls. The Soviet problem was orders of magnitude larger. Anatoly Kitov, heading Computing Center No. 1 for the Ministry of Defense, recognized that off-the-shelf hardware couldn't handle this load. He pushed for purpose-built, high-speed machines, initially used for satellite orbital calculations. In 1959, this extreme calculation requirement manifested in the M100 computer. To reach necessary speeds, Kitov's team implemented a forward-thinking innovation, instruction pipelining. Instead of waiting for an entire instruction cycle, fetch, decode, execute, to finish, the M100 overlapped these stages. As one instruction executed, the next was already being decoded. The direct result of this architecture was a processing speed of 100,000 operations per second, making the M100 one of the fastest computers in the world. Kitov's pipelined design proved that the hardware bottlenecks of early computing could be bypassed entirely through structural redesign. While Kitov was pushing hardware speeds, Viktor Glushkov introduced rigorous mathematical logic into computer theory at the Institute of Cybernetics in Kyiv. His 1961 publication, Synthesis of Digital Automata, changed how computers were conceived and built. This visualization represents Glushkov's method. creating a mathematical abstraction that allowed physical hardware components to be represented strictly by algebraic expressions. Before this, hardware wiring was an ad hoc craft. Glushkov's approach allowed circuits to be derived and proven mathematically before a single wire was soldered. This theory birthed the project system, an early computer-aided design platform that enabled the systematic, software-driven engineering of defense and military computers. Glushkov then pushed this theoretical work toward a completely new structural concept, the macro-conveyor architecture. Traditional computers suffer from the von Neumann bottleneck, where the system is limited by a single stream of instructions interacting with a single stream of data. The macro-conveyor solved this. It was an early form of multiple instruction, multiple data, or MIMD processing. It was designed for limitless scaling, executing numerous independent data streams simultaneously. Glushkov's algebraic methods shifted Soviet computer design into a mathematically rigorous engineering discipline. These advances in hardware served a specific macro network strategy, the Unified State Network of Computing Centers, or USNCC.
This map shows the proposed topology of the USNCC. It was a rigid, top-down networking tree, explicitly designed to mirror the command economy of the state. At its middle tier, the network relied on approximately 100 large regional hubs located in major industrial centers, united by broadband communication channels. Branching down from those regional hubs was the lower tier, 20,000 smaller computing centers located directly at individual factories. Unlike ARPANET, this wasn't a resilient web of nodes, but a rigid vertical tree. Its operational flow was one way, requiring continuous upward reporting of local factory data. There was zero lateral communication. Steel mills spoke to Moscow, not each other. This network was the hardware nervous system for a project called OGAS, a centralized software environment that used macroeconomic models to optimize national production targets. The USNCC and OGAS were the digital mirrors of the centralized Soviet state, operating together as a single distributed supercomputer designed to automate socialism. But this macroscopic vision encountered intense systemic bureaucratic friction that stalled its implementation throughout the 1960s and 70s. The mathematical models of OGAS required absolute algorithmic control and total, unmanipulated data transparency from all industrial sectors. This transparency was politically threatening. Accurate, automated data would expose vast industrial inefficiencies and strip mid-level party officials of their discretionary power and influence. The central planners at the Central Statistical Administration actively fought the project. They understood that automated reporting would bypass their own administrative authority. Kitov and Glushkov had explicitly designed their system to replace traditional political leadership with objective scientific management. The host political system effectively rejected OGAS, terrified that algorithmic transparency would dissolve their authority. The collapse was political, not technological. But while the national network was blocked by political elites, Soviet cybernetic research survived and thrived at the local industrial level. Glushkov and his teams pivoted to deploying automated management information systems across 9 defense and heavy industry ministries. The prime example was the Lviv system, implemented in 1967 at the Lviv television plant. This award-winning system successfully brought automated management to mass manufacturing environments. These localized networks successfully automated scientific research, complex materials testing, and real-time factory processes without needing a national internet to function. Glushkov's engineers built specialized data interfaces and problem-oriented laboratories directly into the factory hardware, closing the loop between physical industrial machines and digital processing. They successfully built isolated, highly advanced industrial control loops. It was empirical proof that their mathematical theories worked flawlessly in applied manufacturing. Today, this early Soviet research finds its closest parallel not in our social media networks, but in the infrastructure of global industry. The true legacy of Kitov and Glushkov lives on in modern enterprise resource planning systems and the automated supply chains that govern the digital economy. Their technical contributions were specific and enduring: structural programming theory, the algebraic design of hardware, and early MIMD scaling architectures.
The absence of a Soviet ARPANET does not erase the massive advancements they made in computational mathematics and industrial automation. The computer-aided design software used to engineer modern microprocessors still relies on the algebraic logic principles first pioneered in Kiev. When measured against its own designed intent, the Soviet digital economy emerges as a profound, if misunderstood, leap into cybernetic engineering. When we look back at the Cold War technology race, the standard history points to one specific American triumph. We see the creation of a decentralized, packet-switching Internet designed to survive a nuclear strike by dynamically routing data across a resilient web. If we look at a map of the Soviet Union from that exact same era, we see a complete void. There is no decentralized web of communication. The territory remains entirely dark and disconnected. This disconnect is often seen as a failure of technical capability. However, Soviet scientists were actually developing some of the most advanced computing systems in the world. Their absence from the public web was not a lack of expertise, but a consequence of how their state chose to apply and restrict the flow of information. Two architects in particular, Anatoly Kitov and Viktor Glushkov, spent decades engineering world-class computing systems meant to run the entire country. Judging Soviet computing by its failure to clone ARPANET misses the actual history. Their innovations were directed elsewhere, toward algorithmic management and hardware architecture, rather than packet-switching communication. In the early 1950s, the Soviet state officially condemned cybernetics as a Western pseudoscience. Research in the field was actively suppressed by the government. That ideological barrier held until 1955, when military scientist Anatoly Kitov published an article titled "The Main Features of Cybernetics." He explicitly defended the discipline and successfully shifted the Communist Party's official stance, opening the door for legitimate research. Kitov expanded the role of the computer beyond ballistic calculations, proposing instead that these machines solve the complex information logical problems required to optimize a national economy. To make this practical, he led the creation of ALGEM, a new algorithmic language specifically designed to program economic and mathematical problems for enterprises across Eastern Europe. By rehabilitating cybernetics, Kitov provided the theoretical clearance required for Soviet scientists to even conceptualize a digitized state. In 1959, Kitov sent a letter directly to Soviet leader Nikita Khrushchev. It contained a proposal known as the Red Book. This diagram illustrates Kitov's core concept, the unified state network of computing centers. This massive digital infrastructure replaced administrative command leadership with scientific management. Notice how civilian and military streams merge into the exact same nodes, maximizing hardware efficiency across the vast Soviet Union. The response from the military and political establishment was severe. Because the proposal openly criticized existing management methods, Kitov was stripped of his prestigious military post and expelled from the Communist Party. The Red Book shows that the USSR had a blueprint for a national digital network years before the West. The leadership prioritized absolute administrative control over systemic optimization. Following Kitov's expulsion, mathematician Viktor Glushkov took over the task of engineering the physical hardware and mathematical models required to process the data of an entire national economy. In this visualization of his 1961 Synthesis of Digital Automata, Glushkov represented physical computer components as algebraic expressions. This rigorous mathematics allowed his team at the Kiev Institute of Cybernetics to systematically design entirely new non-von-Neumann computer architectures from the ground up. To solve single processor limits, Glushkov defined the macro conveyor architecture. This schematic demonstrates multiple independent data and command streams processing simultaneously. This architecture manifested in the ES-2701 supercomputer, breaking the barrier of 1 billion operations per second. Glushkov's algebraic rigor provided a solution to the hardware scaling problem. He successfully proved that the sheer processing power required to run a national economic network was physically achievable. Before attempting a national rollout, Glushkov tested his theories on the ground. In 1967, his team launched the Lviv Automated Management Information System to track and manage the mass production lines at a television plant. The system successfully tracked all enterprise data. Based on that success, Deputy Chairman Alexei Kosygin commissioned Glushkov to design the ultimate macro project, the State Automated Management Information System, known as OGAS. This map outlines the intended topology of OGAS. It required 100 large regional computing hubs in major industrial cities, linked by broadband channels. From these hubs, the network branched out to connect exactly 20,000 distinct enterprise nodes across the country. The data flow was strictly hierarchical. Raw economic reporting data flowed up from the local enterprises to the central hubs, and optimized macroeconomic planning commands flowed back down to the factory floors. OGAS was never meant to be a peer-to-peer communication web like ARPANET. It was engineered as a real-time algorithmic engine to perfectly optimize a rigidly planned command economy. But a technically perfect network cannot fix an inherently misaligned incentive structure. In the planned socialist economy, factory managers were routinely incentivized to hide their inefficiencies to ensure they met state production quotas. This created immediate friction. Average bureaucratic managers actively resisted the implementation of OGAS because strict automated computer tracking would immediately expose their flawed technical and economic indicators. The resistance went all the way to the top of the state. Political leaders, including Leonid Brezhnev, realized that shifting to algorithmic management would strip them of their discretionary administrative power. Bureaucrats mounted a targeted campaign against the project, circulating claims that Glushkov literally wanted a computer to replace the Politburo. As a result, the project was stalled indefinitely in planning committees. The OGAS network perfectly modeled the centralized structure of the Soviet state. It failed because true algorithmic optimization demands total data transparency, a requirement that poses a fatal threat to an authoritarian bureaucracy. The state abandoned the physical infrastructure of the macro network, but the mathematical foundation remained intact within isolated academic centers. In his final years, Glushkov directed this momentum toward theoretical concepts he termed paperless informatics and early frameworks for e-government. Kitov and Glushkov built foundational models for structural pattern recognition, artificial intelligence, and digital administration. Those models survived the collapse of the Soviet Union and actively inform modern information technology today. To dismiss Soviet computing because it never built an internet clone is to overlook its specific trajectory. Kitov and Glushkov drafted the blueprints for a state managed by algorithms, a vision of e-government and digital administration that, while rejected by the Soviet bureaucracy, anticipated the structures of our current digital age. Standard accounts of the Cold War technology race usually conclude with the United States pulling ahead by building ARPANET, the precursor to the modern Internet. Because the Soviet Union never managed to deploy a similar nationwide network, their computing efforts are often written off as a technological failure. This overlooks the fact that Soviet scientists had designed a highly advanced digital infrastructure that predated many Western milestones. Dismissing this history based solely on the absence of a finished network ignores the computer science that was actually accomplished behind the Iron Curtain. Two men stood at the center of this ambition, Anatoly Kitov and Viktor Glushkov, the visionary architects of Soviet cybernetics. They aimed for the total digitization and central management of the entire planned Soviet economy. The mathematical foundations were sound and the blueprints were ready, yet the Soviet Internet was never built. To understand their legacy, we have to look past the network that never materialized and examine the science they managed to create while operating within a rigid regime. Anatoly Kitov began his career as a military strategist who studied forbidden Western texts, specifically those of the American mathematician Norbert Wiener. In 1955, Kitov co-authored the first positive paper on cybernetics in the USSR, helping to reclassify it from a banned pseudoscience to a prioritized field of research. In 1959, he proposed the Red Book, a dual-purpose nationwide network serving both military and the civilian economy through a unified system. For daring to suggest automating administrative control, Kitov was stripped of his military rank and expelled from the Communist Party. He proved the technology was viable, but he also exposed that the Soviet political system would not tolerate the transparency of an automated economy. Viktor Glushkov, a mathematical prodigy, carried the vision forward by developing revolutionary non-von-Neumann computer architectures. He designed a system called OGAS, which was intended to manage the socialist economy using direct data flows instead of top-down quotas. The physical scale was immense. Glushkov's plan involved connecting 20,000 local enterprise nodes to 100 regional data hubs. Under this system, factories could transmit information directly to the central planners, bypassing the mid-level bureaucrats who traditionally controlled the flow of data. This wasn't just a technical blueprint. OGAS represented a direct threat to the Soviet administrative hierarchy. The Central Statistical Administration and thousands of middle management bureaucrats recognized the danger immediately. A computer-managed economy would expose regional inefficiencies and strip these managers of their power to manipulate production numbers. Ultimately, leaders like Leonid Brezhnev rejected the OGAS proposal, choosing a state structure they could control over one that actually worked efficiently. A political system desperate to protect its own flaws killed the Soviet Internet, regardless of the scientific capability available to build it. Glushkov warned that rejecting this digital transition would eventually lead to the collapse of the entire Soviet social system. While the nationwide network died, the localized scientific work of Kitov and Glushkov succeeded. They successfully deployed automated management systems at major sites like the Lviv television plant and the Kuntsevo radio plant, while creating algorithmic languages like Algem that were adopted by hundreds of Soviet enterprises. These localized solutions provided a digital framework for Soviet industrial manufacturing that functioned long after the central network was abandoned. In 1996, the IEEE Computer Society posthumously awarded Glushkov the Computer Pioneer Medal for his work in digital automation. The theoretical foundations laid by both men now support modern Russia's digital economy initiatives. They trained a workforce of 700,000 IT professionals who carried their knowledge past the eventual collapse of the regime. The workforce they built and the theories they proved out outlived the state that tried to constrain them.
When we look back at the Cold War through the lens of modern technology, it is tempting to see a one-sided race. The United States built the foundation of the modern, decentralized Internet, a pulsing network of independent nodes. Because the Soviet Union never produced an equivalent system, the standard historical narrative assumes their computer science program simply failed. Measuring Soviet computing against the American Internet is a category error. It evaluates their engineering against an objective they were actively trying to avoid. Soviet scientists had zero interest in building an open, resilient communication web. Their engineering goal was the construction of a centralized, cybernetic nervous system designed to govern a command economy. This approach was pioneered by two engineers, Anatoly Kitov, a military cyberneticist, and Viktor Glushkov, a mathematician who directed the Institute of Cybernetics in Kyiv. Their ultimate objective was to replace the flawed human bureaucracy of the state with computational logic, automating the management and allocation of every single resource within the national economy in real time. The Soviet Union suffered from a severe deficit in physical microchip manufacturing. To compensate for those hardware limitations, Kitov and Glushkov were forced to develop highly advanced theoretical models of computer science. To understand what they actually built, we have to trace their engineering from the mathematical modeling of a single logic gate, scale up to their parallel processor architectures, and finally examine their blueprint for a nationwide economic network. Evaluating the scale of Soviet computing requires discarding the Western Internet framework entirely. We have to look at their technology strictly as a custom-built engine for a centrally planned state. In 1961, Viktor Glushkov published a monograph titled Synthesis of Digital Automata, addressing a core problem in the design of internal computer structures. Rather than relying on physical breadboards and wiring tests, Glushkov proposed treating physical computer circuits as pure mathematics. He developed a system where the hardware components of a machine were translated into strict algebraic expressions. Using what he called the algebra of regular events, engineers could mathematically prove whether a circuit design would function before a single wire was soldered. If they optimized the algebra, they optimized the hardware. This theoretical rigor was an absolute necessity. The Soviet semiconductor industry could not match the output or quality of American manufacturing, so Glushkov's team had to eliminate inefficiencies at the mathematical level. This algebra became the bedrock for a software system developed at the Institute of Cybernetics known as Project. Project was an early computer-aided design system for computer architecture. It automated the design of new machines based entirely on Glushkov's mathematical frameworks. By abstracting hardware into pure mathematics, Glushkov provided Soviet engineers a way to bypass their manufacturing deficits and conceptualize highly advanced computing architectures. That mathematical foundation allowed them to attack one of the primary hardware bottlenecks of the 1970s, the von Neumann architecture. This diagram highlights the core limitation of a single-threaded von Neumann pipeline. The central processing unit handles only one instruction and one packet of data at a time. Every subsequent task is waiting in line to be processed sequentially. To maximize performance using inferior physical components, Glushkov proposed a radical alternative in the late 1970s that he called the macro-conveyor architecture. In modern computer science, this is known as a multiple instruction stream, multiple data stream architecture, or MIMD. Instead of forcing data through a single CPU choke point, the macro-conveyor system broke problems apart for simultaneous execution across multiple logical blocks. This parallel processing model meant that even if individual processors were slower than Western equivalents, clustering them to execute tasks simultaneously produced immense computational throughput. The hardware built on these principles, specifically the ES2701 and the EU1766 supercomputers, successfully broke the performance barrier of 1 billion operations per second. Soviet supercomputing speed was not derived from superior silicon fabrication. It was the direct result of mathematical routing and highly efficient parallel architectural design. Having optimized the logic inside the processor, Soviet scientists then applied these exact principles to the physical production lines of the state.
They developed Automated Management Information Systems, known as ASU. These acted as the direct predecessors to the enterprise resource planning software used by global corporations today. Anatoly Kitov was the primary architect of operationalizing these localized enterprise systems for the industrial sector. To make this possible, Kitov engineered a specialized algorithmic programming language called Algem. While most early programming languages were designed for scientific calculation, Algem was strictly built to compute economic modeling, inventory logistics, and mathematical planning problems. In 1967, Glushkov and Kitov deployed an ASU at the Lviv television plant. It operated as a functioning cybernetic factory, with inventory levels and production output data continuously pinging into a localized computing center to optimize the manufacturing schedule. This localized model proved highly efficient. It was standardized across numerous mass production facilities and adopted by 9 separate defense ministries. By applying computational logic to the factory floor, Soviet engineers created highly functional, data-driven production nodes that automated resource management at the enterprise level. The final engineering objective was to take these thousands of isolated factory nodes and fuse them into a single, synchronized national network. As early as 1959, Anatoly Kitov submitted the Red Book project. It was the first concrete technical proposal for a unified, nationwide computer network. Kitov proposed a dual-purpose network of computing centers that would seamlessly integrate military defense calculations with civilian economic planning, sharing data across the continent. These massive proposals for a centralized, automated economy were first debated during Nikita Khrushchev's tenure as premier. While Kitov's initial proposal was dismissed, Viktor Glushkov refined and massively expanded the concept in the 1960s into a project called OGAS, the State Automated Management Information System. The topology of OGAS was rigid and hierarchical. It proposed linking 20,000 local enterprise centers to 100 massive regional computer hubs. These hubs would then pipe data directly into a central administration node in Moscow. Glushkov designed the network to use broadband communication channels and message switching. The goal was to collect national production data and execute macroeconomic models in real time, operating the Soviet economy as one massive algorithm. While the technical design for OGAS was sound, the project was dismantled by bureaucratic self-preservation. Mid-level administrators within agencies like the Central Statistical Administration recognized that mathematical transparency would expose local inefficiencies and strip away their administrative power. They actively campaigned against the project to protect their own influence. The OGAS blueprint offered a highly efficient economic model, but it demanded a level of exact mathematical transparency that directly threatened the existing command-driven political hierarchy. The network was stalled and then quietly abandoned. The sequence from microscopic algebraic equations to the unlit map of the national network defines the full scope of the Soviet cybernetic project. Glushkov and Kitov authored the mathematical proofs that treated physical hardware as algebra, and they engineered advanced parallel hardware architectures capable of 1 billion operations per second. Their localized management systems were successfully installed to regulate and optimize physical manufacturing plants across multiple industries. The ultimate failure occurred at the highest levels of Soviet leadership, under figures like Alexei Kosygin, where the political capital required to force the national network past entrenched bureaucrats simply did not exist. This political failure at the top obscures the rigorous foundation of technical research produced by the Soviet cybernetic institutes. Building a national network was an engineering possibility that ultimately failed in the face of political resistance. Long after the national network projects died, Glushkov and Kitov continued to pioneer fields like associative programming, informatics, and medical cybernetics. Their students and the research institutes they established continued to drive global computer science development well beyond the collapse of the Soviet Union. Today, those foundational theoretical frameworks remain deeply embedded in the bedrock of modern Russian digital infrastructure and IT systems. The Soviet computing program did not fail to understand the future of digital networks. The political state simply failed to adapt to the cybernetic reality its own engineers had built.
In 1957, the Soviet Union launched the Sputnik satellite. They established an early dominance in the aerospace engineering of the Cold War. Yet, if you examine the dominant Western historical record regarding Soviet computing, the consensus is that their hardware and software sectors were systemic failures. That judgment of failure rests almost entirely on a single missing achievement. The Soviets never built a piece of hardware like this interface message processor, the physical foundation of the American ARPANET. ARPANET was designed as a decentralized peer-to-peer communication web. Its primary utility was allowing independent researchers to share data across distances, without a central node dictating the flow. Judging Soviet computing by its failure to build a decentralized network is a category error. You are testing them against a rubric they explicitly rejected. Soviet computer scientists were never trying to build a horizontal communication web for academics. This diagram highlights the architectural contrast. On the left is the American ARPANET model. On the right is OGAS, the Soviet ambition. They sought to build a fully automated, cybernetic macro architecture designed to govern the entirety of a planned national economy. This hierarchical structure was engineered to ingest national production data in real time, routing every metric of industrial output to a central processing core. To accurately assess the legacy of Soviet computing, we have to stop looking for a missing decentralized internet. We need to analyze the blueprints of the digital economy they actually attempted to construct. Designing a macro architecture to run a national economy requires a rigorous mathematical foundation. In 1961, mathematician Viktor Glushkov provided that foundation. He developed a theoretical framework that treated physical computer hardware as pure mathematical abstractions. He called this concept the synthesis of digital automata. It allowed engineers to represent physical computer components, like logic gates, as algebraic expressions. By translating hardware into algebra, Glushkov enabled the rapid, theoretical design of new computer structures without having to physically build prototypes first. While Glushkov was finalizing this theoretical math in Kiev, engineer Anatoly Kitov was already applying advanced architectures to physical hardware in Moscow. Kitov led the development of the M100, a specialized military computer officially deployed in 1959. The M100 featured a major architectural innovation, instruction pipelining. This diagram shows the mechanics of that pipeline. Instead of waiting for one instruction to completely finish processing before loading the next, pipelining allows for overlapping execution. Multiple instructions move through different stages of the processor simultaneously. Implementing this pipeline allowed the M100 to execute 100,000 operations per second, the highest recorded speed in the Soviet Union at the time.
By 1960, the Soviets possessed both the abstract algebraic methods to design complex systems and the physical hardware architectures to execute them at high speed. The engineering challenge was scale. Managing localized math is one thing. Managing a command economy spanning 11 time zones is another. Glushkov began by proving his concepts at the micro level, designing automated management systems for individual enterprises. In 1967, his team launched the Lviv system.
It was installed at a television manufacturing plant to completely automate the production tracking and logistics. Anatoly Kitov had already proposed scaling this concept nationwide in 1959. His Red Book project advocated for a unified, dual-use network of computer centers to serve both the military and the civilian economy. Glushkov absorbed and refined Kitov's ideas into the 1962 OGAS proposal. The technical backbone of this proposal was the unified state network of computing centers. This maps the architecture. At the base, 20,000 nodes in factories collected raw data. These nodes fed upward over broadband into 100 regional hubs in industrial cities. Finally, the aggregated data flowed to a centralized macroeconomic core in Moscow, providing a real-time economic snapshot. The objective was to eliminate human central planners, relying on algorithms to calculate resource allocation without guesswork or local bias. OGAS was a statewide enterprise resource planning system. It was an instrument engineered to mathematically optimize the survival of the state. OGAS was never built. The project was buried in endless committees, and Anatoly Kitov was expelled from the Communist Party for repeatedly criticizing the existing management structure. The rejection of this nationwide network was not caused by flawed physics, a lack of mathematical theory, or insurmountable hardware constraints. The architecture of the network perfectly mirrored the centralized power structure of the Soviet state, yet the state viewed it as a mortal threat. The friction came from the middle bureaucracy, specifically the Central Statistical Administration. In the command economy, massaging quotas and manually interpreting data was the currency of political survival. An automated network piping real-time, unfiltered data to Moscow stripped these mid-level officials of their power. The resulting conflict pitted young, data-driven technocrats demanding algorithmic transparency against an aging political elite defending its right to opacity. OGAS was killed because an algorithm requires accurate data to function, and the Soviet administrative command system relied on the power to manipulate the truth. If we move the timeline forward to the late 1970s and 1980s, we see the aftermath of the OGAS rejection. The state abandoned the unified national network, but the underlying scientific push for automation resulted in a massive domestic industry. By the late Cold War, the Soviet IT sector employed over 700,000 people, deploying localized automated management systems across major industries. Viktor Glushkov maintained his theoretical focus, directing his institute to design highly advanced non-von-Neumann computer architectures. This visualization represents the MIMD architecture, multiple instruction, multiple data streams. Glushkov's team applied this concept to the ES2701 macro conveyor, splitting processing tasks into parallel, independent pathways to eliminate central bottlenecks. Utilizing this parallel structure, late-era Soviet supercomputers broke the performance boundary of 1 billion operations per second. Framing this era of computer science as a failure, simply because it did not yield a decentralized internet, ignores the actual historical output. The legacy of Kitov and Glushkov is the establishment of digital automata theory, high-speed instruction pipelining, and the earliest, most rigorous architectural blueprints for a modern digital economy. The standard historical narrative of Cold War computing is a stark contrast. In the West, engineers successfully built the decentralized ARPANET. In the Soviet Union, parallel attempts to build a nationwide network sparked, sputtered, and went dark. But framing Soviet computing as a failed internet assumes their engineers were trying to build a peer-to-peer communication web. They weren't. Decades of Cold War secrecy and language barriers left Western technology historians evaluating Soviet network projects through an exclusively American lens. The actual objective was the engineering of a cybernetic command economy. Judging Soviet computing by its lack of a public internet overlooks the rigorous systems architecture that defined their actual research. The theoretical foundation for this cybernetic movement was built by two men, Anatoly Kitov and Viktor Glushkov. Their engineering objective was to construct a unified mathematical engine capable of running a massive national economy in real time. The ultimate culmination of their theories was a project known as OGAS, the State Automated Management Information System. OGAS was designed for absolute, mathematically optimized, top-down resource allocation. Examining the blueprints of OGAS and its predecessors reveals the conceptual architecture of the modern digital economy. In the 1950s, Anatoly Kitov headed Computing Center No. 1, directing Soviet military computational efforts. His primary focus was calculating complex missile and anti-aircraft ballistics. At the time, state ideologists officially classified cybernetics as a Western pseudoscience, restricting its academic study. Kitov recognized that the exact same computational logic used to model ballistic trajectories could be repurposed. Instead of calculating physical vectors, computers could model and optimize the flow of national resources. In 1959, Kitov bypassed traditional channels and sent a proposal directly to Soviet leader Nikita Khrushchev. This document became known as the Red Book Project. The core of this proposal was the creation of the unified state network of computing centers. This network was designed to be dual-purpose. It would serve military logistics while simultaneously processing raw economic data from civilian enterprises across the entire Soviet territory. The proposal was rejected, and Kitov was dismissed from his post. Optimizing state data meant challenging the existing administrative hierarchy, and technical elegance was insufficient to overcome political inertia. As Kitov's proposal stalled, Viktor Glushkov published his 1961 work, Synthesis of Digital Automata. This work shifted hardware design from physical engineering toward formal logic. By submitting computer components as algebraic expressions, Glushkov allowed engineers to treat hardware architecture as verifiable mathematical proofs. Glushkov understood that calculating the variables of an entire national economy required hardware capable of processing massive amounts of data simultaneously. Traditional von-Neumann computer architecture, which processes commands sequentially, was simply too slow. His team developed a macro-conveyor architecture, utilizing what is now classified as a multiple-instruction, multiple-data framework. This principle bypassed the sequential bottleneck, allowing the system to process vast arrays of independent data streams and commands in parallel. The resulting hardware scalability was immense. Systems designed under this architecture achieved a capacity of 1 billion operations per second by the 1980s. Glushkov's abstract mathematical theories provided the specific framework required to scale physical hardware to the logistics of a global superpower. In 1962, state officials, including Deputy Chairman Alexei Kosygin, commissioned Glushkov to draft the architecture for the State Automated Management Information System, or OGAS. Looking at the structural diagram of this network illustrates the difference between Western networking logic and Soviet command structure. At the top of the OGAS hierarchy were roughly 100 large regional processing hubs, linked by broadband message switching channels. These primary hubs spider-webbed downward, connecting to 20,000 localized enterprise and factory nodes at the base. Real-time reporting information on inventory, production, and resources flowed strictly upward from local nodes into the regional centers. The hubs would compute macroeconomic models against this data, generating optimized central planning directives that were transmitted back down the chain of command. This was a closed-loop optimization cycle. It was not built to facilitate open communication between nodes, but to calculate the most efficient distribution of materials across a continent. Engineers designed OGAS as a specialized digital nervous system, a mechanism built for the total automation of a centralized state. If OGAS was specifically engineered to optimize the Soviet command economy, we have to ask why the draft submitted in 1964 was met with sharp objections and ultimately stalled. The answer lies in the data paths. The cybernetic model inherently bypassed mid-level bureaucracy, routing raw data directly past institutions like the Central Statistical Administration. Total digital automation rendered layers of middle management obsolete. To the entrenched Communist Party leadership, this efficiency was a direct threat to their political power base. Adopting OGAS meant the party would have to cede administrative control to algorithms and a rising class of young technocrats. In response, state administrators weaponized arguments regarding the project's high cost and technical complexity, successfully delaying its implementation indefinitely.
The network's design correctly reflected the rigidly centralized nature of the Soviet state. Ironically, that exact accuracy triggered an immune response from the administrators who operated that structure. OGAS failed because it was a technological solution to a problem the political state refused to solve. The nationwide macro network was blocked, but the underlying microsystems successfully infiltrated the Soviet industrial base. Deprived of a national grid, Glushkov and his engineers shifted their focus to localized factory optimization, creating Automated Management Information Systems, or AMIS. These systems yielded specific, measurable successes, such as the Lviv system, which used computers to manage steel smelting and production logistics at massive scale. These localized implementations, powered by Kitov's standardized Algem programming language, coordinated production schedules, inventory, and labor across hundreds of diverse enterprises. This synthesis of disparate business functions into a single data model established the functional architecture used by modern enterprise resource planning software. Kitov and Glushkov successfully deployed standardized versions of these management systems across 9 defense ministries and countless civilian sectors. Their foundational research continued to drive early frameworks for artificial intelligence, structural pattern recognition, and non-von-Neumann computing architectures. The architectural blueprints for the digital command economy remain the primary legacy of Soviet computing, a centralized systems logic that persists in the massive corporate data networks operating today.
The history of computing often writes off the Soviet Union as a failure because they never built an open, decentralized internet like ARPANET. But consider the geography. Networking the Soviet Union meant laying data lines across 11 time zones and a sixth of the Earth's landmass. Judging Soviet computing by the absence of a public internet misreads their entire objective. They were not trying to build a resilient communication web. In the late 1950s and 60s, scientists like Anatoly Kitov and Viktor Glushkov looked at computer networks and saw a different utility. They drafted proposals for the Unified State Network of Computing Centers, or EGSVC, which would serve as the backbone for a massive system called OGAS. OGAS was designed to be a national-scale enterprise resource planning system. The goal was to mathematically model the entire Soviet economy in real time. A communication network routes messages between individuals. A macroeconomic optimization network ingests raw industrial data, calculates demand, and allocates physical resources across a continent. The physical network of OGAS ultimately stalled in the halls of Soviet bureaucracy. Yet the engineering required to even attempt it yielded remarkable hardware and software. To process that volume of data, Soviet engineers had to advance the fields of automata theory and pioneer non-von-Neumann computer architectures. While the physical network was never completed, the project forced a series of advancements in automata theory and architecture that would define Soviet computing for decades. In 1954, Anatoly Kitov took command of Computing Center No. 1. His teams ran the calculations that put the first Sputnik satellites into orbit. In the mid-1950s, Kitov pioneered the concept of non-arithmetic applications. He advocated for using computing power for logical operations, specifically targeting administrative management and economic planning. In 1959, he submitted the Red Book project to Soviet leadership. He outlined a dual-purpose network of computing centers that would manage both military defense and civilian industry. The proposal triggered an immediate backlash. Moving economic data through an automated, transparent system threatened the existing administrative command structure. Mid-level bureaucrats realized a computer would quickly expose manufacturing inefficiencies and inflated production quotas. Top Soviet leadership rejected the Red Book, expelled Kitov from the Communist Party, and removed him from his post. Kitov's proposal initiated a decades-long conflict inside the USSR, technocratic efficiency pushing against entrenched political power. While Kitov fought the political battle, Viktor Glushkov recognized that building a national network required a completely new theoretical foundation for computer hardware. In his 1961 work, Synthesis of Digital Automata, Glushkov introduced a method to treat a physical machine as a strict mathematical abstraction. By representing physical computer components as algebraic expressions, complex hardware could be designed programmatically. This algebraic theory drove the creation of the Project CAD systems at the Institute of Cybernetics. computer design shifted from manual electrical wiring to software-driven engineering. Engineers could draft and test highly complex architectures before manufacturing a single part, allowing for rapid scaling into massive industrial production. Glushkov's mathematical framework allowed Soviet computer design to scale conceptually before it had to scale physically. In 1962, state planner Alexei Kosygin authorized Glushkov to draft the architecture for the State Automated Management Information System, or OGAS. Glushkov designed a rigid, top-down hierarchy.
At the peak sat the State Planning Committee in Moscow, branching down to roughly 100 regional hubs. From those hubs, the network splintered outward to connect 20,000 localized endpoints at factories, farms, and enterprises. The design required a continuous upward flow of data. Every factory streamed raw production numbers, inventory levels, and labor statistics up to the central hubs. The mainframes processed this data through macroeconomic models, then transmitted optimized targets back down to the edge nodes. OGAS was not built for conversation. It was a continent-wide feedback loop designed to dictate resource allocation. Calculating optimal resource distribution for an entire superpower created a massive computational bottleneck. Traditional sequential processing, where a computer executes one instruction at a time, was simply too slow to run macroeconomic models for thousands of factories simultaneously. Glushkov's team bypassed this limit by developing a macro-conveyor architecture. This multiple instruction, multiple data structure processed different massive data sets in parallel through independent pipelines. This hardware milestone culminated in systems like the ES-2701 supercomputer, which broke the barrier of 1 billion operations per second. The hardware was capable, and the mathematical models were sound, yet the full OGAS network stalled. The Central Statistical Administration actively blocked the project. An automated system would eliminate the ability to manually adjust numbers, stripping the aging Soviet elite of their primary mechanism for political control. The political apparatus ultimately crushed its own technological salvation. Achieving true economic efficiency meant the leadership had to sacrifice absolute authority. The United States built ARPANET as a decentralized web to ensure communication survived a nuclear strike. The Soviet Union designed OGAS as a centralized nervous system to optimize a planned economy. The Soviet state project failed, but its hierarchical architecture perfectly mirrors the data structures of modern corporate cloud platforms. A central data lake ingests real-time analytics from thousands of edge compute nodes, optimizing supply chains and labor allocation from the top down. The Soviet state desperately needed a system like OGAS to manage its unwieldy planned economy, but its leaders feared the exact operational transparency the system required to function. The continent-wide cables were never fully laid, but the theoretical groundwork in digital automata and automated industrial management survived, advancing computer science globally. Kitov and Glushkov left behind the foundational blueprints for the digital economies and enterprise networks that govern the modern world. Standard histories of the Cold War often frame it as a race. The West built the ARPANET, a decentralized network designed for resilience, while the Soviet Union struggled and ultimately failed to produce a peer. Evaluating Soviet computing by how closely it resembled the ARPANET ignores the specific technical goals of the designers. Their objective was not to build a communications web for individuals. The OGAS architecture proposed something different, a massive hierarchical tree structure. This was a plan for a nationwide enterprise resource planning system, a tool to mathematically optimize the command economy in real time. By examining the technical blueprints of the Red Book and OGAS projects, we can trace how these scientists intended to transition the Soviet Union into a computer-managed state. These cybernetic projects were a deliberate attempt to build a unified digital operating system for the entire national infrastructure. In the late 1960s, Soviet cybernetics focused on the science of information processing as a way to manage complex organizations. To them, the national economy was a vast system that could be controlled through data. In 1961, Viktor Glushkov achieved a breakthrough, the synthesis of digital automata. He proved computer hardware could be modeled as abstract algebraic expressions.
This mathematical model allowed engineers to use algorithms to automatically generate specialized hardware blueprints. Managing a national resource grid meant processing information at a scale standard mainframes couldn't handle. This mathematical control allowed designers to custom engineer the high-capacity hardware required to manage that massive volume of data. Anatoly Kitov made the first attempt to implement this at a national level in 1959. His Red Book proposal outlined a unified state network of computing centers. Kitov proposed a dual-purpose architecture. The network would allow the military sector and the civilian economy to share mainframe computational cycles and data reserves within a single centralized cluster. Kitov wanted decisions driven by real-time economic modeling rather than bureaucratic intuition. But the proposal was rejected. Bureaucratic leaders were reluctant to relinquish control to a centralized algorithm. Kitov was removed from his post and expelled from the party. In 1962, the mandate for a national network passed to Viktor Glushkov. His project was the State Automated Management Information System, known by its Russian acronym, OGAS. This rigid three-tier architecture branched from a master node in Moscow to 100 regional centers, connecting to 20,000 localized factory terminals. Data flowed strictly through this hierarchy. Production reports pulsed upward to the center, where computers calculated planning commands and pushed them back down. Because OGAS was built for predictable, continuous streams of economic reporting, Glushkov developed specialized operating systems. This was a divergence from the packet switching protocols being refined in the West. OGAS was an integrated economic calculator for the state, a system where data moved through a fixed hierarchy to serve central planning. Calculating a national plan in real time required massive processing power. By the early 1960s, the physical limitations of these standard single-file mainframes were rapidly becoming an impossible bottleneck for the state. Standard computers followed the von-Neumann architecture, creating a massive single-file bottleneck when processing simultaneous reports. Glushkov's solution was the macro-conveyor architecture. This multiple instruction, multiple data structure allowed massive streams of economic data to be processed in parallel. This shift in architecture led to the creation of high-performance systems like the ES2701 and EU1766, which eventually broke the barrier of 1 billion operations per second in the USSR. These scientists successfully engineered non-von-Neumann computing systems specifically to meet the mathematical demands of a national planned economy. The ultimate reason OGAS was never fully implemented was not a lack of hardware or mathematical skill. The project faced a political paradox. The algorithmic efficiency and data transparency OGAS offered threatened the very bureaucracy it was supposed to serve. If a computer could optimize the economy, the thousands of officials managing it would be redundant. State bodies and individual bureaucratic units resisted and delayed the project to protect their own authority, eventually dismantling the effort from within. The legacy of Kitov and Glushkov rests in the theoretical groundwork they established for modern digital economies. They produced the first functional blueprints for e-government and corporate resource planning decades before the political will existed to implement them. The history of computing shows that there is no single inevitable timeline. Instead, there are multiple different architectures, each designed to solve the specific problems of the systems that built them. In 1969, the U.S. linked its defense mainframes into ARPANET, lighting up the first internet nodes. Across the globe, the Soviet map remained entirely dark. Conventional historical accounts suggest that Soviet computer science lacked the technical maturity to support a nationwide network. That assumption is directly contradicted by the work of Soviet pioneers Anatoly Kitov and Viktor Glushkov. During the 1960s, these scientists engineered comprehensive blueprints for a digitized, centrally planned economy that functioned decades ahead of Western equivalents. They called this architecture the Unified State Network of Computing Centers, or USNCC. High-capacity transmission and technical viability were well within reach of Soviet mathematics, but the network shattered because the optimized digital system hit an unsurmountable wall, the entrenched bureaucracy of the Soviet state. The theoretical rigor of the project began with Viktor Glushkov's 1961 work, Synthesis of Digital Automata.
Glushkov used abstract algebraic methods to map software algorithms directly into physical hardware structures. These mathematical proofs powered Project CAD systems, which allowed Soviet computers to automate the design of their own successor circuitry. Anatoly Kitov anchored this hardware evolution in the high-stakes world of military ballistics and anti-aircraft trajectory calculation. In 1959, Kitov's M100 computer introduced conveyor instruction processing to the Soviet Union, a breakthrough now known as pipeline architecture. Glushkov later pioneered the MIMD macroconveyor, an architecture that processed multiple distinct streams of data through parallel instruction pathways simultaneously. This parallel approach allowed machines like the ES-2701 to break the barrier of 1 billion operations per second. Soviet scientists possessed the advanced non-von-Neumann architectures required to run the data-heavy operations of a digital state. By the mid-1960s, these micro-architectural successes were scaled up for industrial deployment. The Soviet Union implemented automated management information systems across major industrial sectors. These functioned as the world's first massive-scale enterprise resource planning systems. At the Lviv television plant, raw production data flowed from assembly line nodes directly to a central mainframe. The mainframe processed this data to calculate and transmit real-time adjustments back to the assembly line, optimizing the factory's output on the fly. Beyond the factory floor, automated laboratories linked remote testing rigs to supercomputers, allowing for live experimental tuning during complex physics and biology research. These localized networks proved that digital command systems were capable of managing complex industrial processes. Managing a centrally planned state economy required more than isolated industrial networks. Anatoly Kitov addressed this with the Red Book project, proposing a dual-purpose network for both military and civilian resource management. Viktor Glushkov expanded this vision into OGAS, the State Automated Management Information System. The OGAS topology relied on 100 large regional computing mainframes situated in major industrial hubs. These regional hubs connected to 20,000 local enterprise nodes at the factory and farm level. High-speed broadband channels utilized message switching to move data packets from local enterprises up to the regional hubs. Finally, those regional hubs flowed their aggregated data directly into a central management apex in Moscow. The system applied continuous mathematical modeling to this unified national data pool to optimize the entire economy in real time. OGAS provided a technically viable blueprint for the world's first fully digital command economy. The transition from technical blueprint to physical implementation was blocked by the institutional reality of the Soviet state. A digital economy requires absolute data transparency and automated resource allocation. This level of transparency stripped the Soviet political leadership of their primary tool for maintaining power, the manual, opaque control of resources. The project hit a wall at the Central Statistical Administration and within key departments of Gosplan. Middle management bureaucrats realized that if OGAS successfully automated the planning process, their own administrative roles would vanish. Administrative committees intentionally buried the network in paperwork and denied its funding. Denied the political will to implement it, the nationwide network gradually dimmed and powered down to black. When a mathematically optimized network threatens the power of the administrators, the bureaucracy will inevitably reject the system. Dismissing the Red Book and OGAS projects as total failures ignores the massive scale of what they actually built. The sheer ambition of these projects forced the Soviet Union to build a domestic IT industry from the ground up. This era left behind a massive human capital legacy. 700,000 IT workers, the Glushkov Institute of Cybernetics, and dedicated computing faculties across the nation. The students of Kitov and Glushkov continued to advance research in cybernetics, systems engineering, and artificial intelligence long after the Cold War ended. The construction of a digital state depends on institutional alignment as much as high-performance hardware and elegant mathematics. The ultimate fate of OGAS proves that a technical architecture must align with the institutional architecture it serves, or it will be destroyed from within.
In the standard history of the information age, the United States built the ARPANET, wiring the continent and triggering a global technological revolution. The Soviet Union, isolated and technologically stagnant, entirely missed the networking era. Look at the vast expanse of the Soviet state during the Cold War. and Western observers often diagnose a condition known as the Internet, an assumption that Soviet computer scientists simply lacked the hardware, the software, and the theoretical capacity to build a national network. But the archives show a different reality. Detailed blueprints for a nationwide, high-speed digital economy were drafted and proposed as early as 1959, decades before the World Wide Web. The absence of a Soviet Internet was a deliberate choice. A state rigidly controlled by human administrators found itself staring at algorithms capable of managing the economy in real time, and it chose to kill the machine rather than share the power. Two computer pioneers drove this vision: Anatoly Kitov and Viktor Glushkov. In 1959, Kitov wrote directly to the Soviet leadership proposing a radical restructuring of the national economy. He argued for stripping away the traditional administrative command style of leadership and replacing it with a scientific framework driven by economic modeling and mathematics. They engineered a real-time macroeconomic management machine, a system that ingested raw production data to compute optimal resource allocation and instantly directed factory floors across 11 time zones. To comprehend why the Soviet bureaucracy viewed this project as an existential threat, we have to look closely at the scale and mathematical rigor of the architecture Kitov and Glushkov actually designed. Kitov detailed his initial framework in what became known as the Red Book project. It outlined the Unified State Network of Computing Centers, or USNCC, conceived as a dual-purpose digital grid to serve both the armed forces and the civilian economy. The technical specifications required broadband communication channels to handle high data volumes, utilizing early forms of message switching to route information efficiently without maintaining continuous physical connections between endpoints. The topology called for exactly 100 regional computing hubs in key industrial cities. From those hubs, the network branched down to 20,000 factory computing centers. Local metrics traveled up to the hubs, and optimized planning models flowed directly back down. Viktor Glushkov took Kitov's logic and scaled it into a comprehensive state proposal known as OGAS, the State Automated Management Information System for the national economy. This design required no theoretical leaps in physics. The OGAS topology provided a structurally sound, highly rational blueprint for a digital economy that rivaled any networking project emerging in the United States. Evaluating OGAS requires looking at the hardware inside early Soviet computing centers. These massive installations were fully capable of running complex military and industrial calculations. The constraint was scaling this hardware efficiently. In 1961, Glushkov published his research on the synthesis of digital algebra, applying algebraic methods to mathematically abstract the physical components of a computer. Most global computing relied on standard sequential processing, the von-Neumann architecture. It forces data to wait in line, processing instructions one at a time, creating a severe bottleneck as data loads increase. Glushkov bypassed this bottleneck entirely with the macro-conveyor architecture. By splitting a single data stream into multiple concurrent pathways, he developed an early framework for MIMD parallel processing. This theory eventually materialized as the EU1766 supercomputer configuration. Operating on a strictly non-von-Neumann architecture, these macro conveyor systems pushed Soviet computing past the barrier of 1 billion operations per second. Isolated from the rapidly iterating Silicon Valleys of the West, Soviet scientists leaned into mathematical abstraction. They designed parallel processing frameworks that achieved high-performance computing through superior logic rather than relying on brute force hardware iteration. The mathematical proofs and hardware capabilities were established. The next variable was whether these automated systems could actually interface with the messy reality of Soviet industrial production. In 1967, Glushkov's team installed the Lviv system at the Electron television plant, wiring the factory line directly into a digital oversight network. This operated as an ASU, an automated management information system. It tracked materials, monitored output, and managed logistics in real time, functioning as a highly advanced precursor to modern enterprise resource planning software. Production efficiency at the Lviv plant spiked. The design was so effective it was standardized into the Kuntsevo system and deployed across 9 separate defense ministries to manage large-scale military manufacturing. These factory-level systems proved that the software, and the hardware, and the underlying algebraic logic all performed as specified. The barrier to scaling this success did not exist inside the laboratory. The true obstacle was the structure of the Soviet state itself. Implementing OGAS meant replacing human decision-making with algorithmic precision, effectively stripping power away from the ideological administrators. Resistance began in the middle ranks. Agencies like the Central Statistical Administration controlled the state by controlling data. To maintain their relevance, these competing administrative fiefdoms suffocated the transparent network, aggressively blocking the data pipelines required to link the regional hubs. At the top, the political calculus was equally severe. Leadership under Leonid Brezhnev understood that a digitally optimized state meant handing power to young mathematical technocrats. State-aligned critics launched disinformation campaigns targeting Glushkov, circulating claims that his project was designed to literally replace the Politburo with a computer. The OGAS network was quietly dismantled. The Soviet bureaucracy correctly diagnosed that total algorithmic efficiency would render the entire political class obsolete. Kitov and Glushkov engineered a digital nervous system fully capable of stabilizing the planned economy. Confronted with a choice between technological survival and maintaining their own authority, the managers of the state chose comfortable stagnation. The physical web of the US NSCC was never completed, but examining the isolated engineering efforts behind the Iron Curtain reveals a massive scientific yield. Glushkov's early work defining the algebra of regular events directly anticipated the global evolution of structural programming, arriving at the exact same logical conclusions as Edsger Dijkstra years before they became industry standards. The computer-aided design methodologies developed in Kyiv, alongside the theoretical proofs for MIMD parallel processing, established the base architecture for modern high-performance supercomputing. The localized automated systems deployed in factories across the region trained hundreds of thousands of engineers, forming the human baseline for the massive IT industry that emerged across Eastern Europe after the Cold War. The Soviet Union failed to network its nation, but the rigorous mathematical blueprints drafted by Kitov and Glushkov pioneered the specific logical structures, from parallel processing to structural programming, that became the technical reality of the digital age.
Look at a map of global computing networks during the Cold War, and the Soviet Union appears entirely dark. The standard historical assumption follows a simple logic. Because the Soviets failed to build a nationwide computer network like ARPANET, their computer science programs were primitive or derivative. The historical record shows otherwise. The failure to network the Soviet state was the result of a deliberate bureaucratic rejection, not a deficit in computational engineering. Behind the Iron Curtain, within the rigid confines of the Soviet state apparatus, two pioneers, Anatoly Kitov and Viktor Glushkov, developed world-class computing theories. Operating out of the Ministry of Defense and the Kiev Institute of Cybernetics, they built mathematical frameworks for hardware synthesis, deployed early enterprise resource planning systems, and engineered advanced non-von-Neumann supercomputer architectures. Judging Soviet computing solely by the absence of an ARPANET equivalent obscures decades of rigorous theoretical computer science. In the early 1950s, the Soviet computing baseline was strictly mathematical. Machines were utilized almost exclusively as arithmetic calculators, tasked with processing military ballistics and nuclear physics data. Anatoly Kitov recognized this limitation. In 1955, he co-authored a paper to officially rehabilitate cybernetics, a field previously dismissed by state ideologists as a capitalist pseudoscience. Kitov redefined the machine's role. He proposed that computers move beyond arithmetic to operate as dynamic information logical processors, systems capable of managing complex administrative and production tasks through continuous feedback loops. By 1959, he translated this to the state level with the Red Book project, proposing a dual-purpose network where military and civilian hubs share data streams, converging into central nodes. Kitov was architecting the world's first blueprint for a centralized, fully digitized national economy. While Kitov mapped the network topology, Viktor Glushkov focused on the physical machines required to run it at the Kiev Institute of Cybernetics. In 1961, Glushkov published a foundational text, Synthesis of Digital Automata. The text detailed a specific engineering logic. Glushkov applied strict algebraic methods to computer architecture, treating physical hardware components, like logic gates and circuits, as mathematical abstractions.
This allowed Soviet engineers to mathematically prove a circuit's efficiency on paper before physical construction. If equations simplified logically, that simplification dictated how to physically optimize the hardware layout. Applying these algebraic proofs directly to the engineering workflow led to the creation of the project systems, a framework that served as one of the earliest instances of computer-aided design for hardware. Glushkov elevated computer engineering from a mechanical assembly task into a rigorous mathematical science, establishing the strict logic required for advanced supercomputing. That mathematical rigor allowed Soviet engineers to accurately predict the impending physical limits of standard computing architectures. Specifically, they identified the von-Neumann bottleneck. A single instruction, single data stream inherently chokes on national-scale data loads. Glushkov's macro-conveyor architecture, a multiple instruction, multiple data framework, split the bottleneck, processing parallel streams simultaneously. By the 1980s, this architecture resulted in physical triumphs. Systems like the ES2701 and the EU1766 broke the 1 billion operations per second processing barrier. These massive processing capabilities were directly deployed into the civilian sector through automated management information systems. At facilities like the Lviv television plant, these systems acted as highly structured enterprise resource planning tools, managing complex manufacturing logistics for massive industrial plants. Soviet engineers successfully matched high-performance, parallel supercomputing with complex industrial logistics, operating entirely independently of Western network development. The culmination of Glushkov's theoretical mathematics and hardware engineering was the blueprint for the OGAS network. OGAS mapped out a massive, highly structured topology. It connected 20,000 local manufacturing nodes, flowing clean data upward into 100 regional computing centers. The objective was to achieve real-time, optimized reporting, planning, and modeling for the entirety of the Soviet planned economy. Despite OGAS being the ideal mechanism for a planned economy, it was deliberately killed by the Soviet state itself. The system required transparent data flow, directly threatening the opacity of mid-level reporting within the Central Statistical Bureau. Central planners realized that total mathematical automation would strip them of their power to obscure production inefficiencies and manipulate factory quotas. The Soviet network didn't fail due to a lack of technical capability. It failed because the proposed network functioned far too objectively for a political system completely reliant on obscure data. Equating the lack of a Soviet internet with a lack of Soviet computer science is an error in technological history. The engineering triumphs are concrete. Kitov and Glushkov deployed early enterprise resource planning systems, engineered advanced MIMD hardware, and successfully synthesized digital automata through pure mathematics. Before his death, Glushkov outlined a vision of paperless informatics, the inevitable digitization of all societal and administrative data. It was a concept detailed decades ahead of global trends. Their academic descendants continue to drive global research in computer science, artificial intelligence, and structural pattern recognition today. The Soviet bureaucracy successfully crushed the physical network, but the immense theoretical rigor of the Soviet Cybernetics school laid an invisible, mathematically profound foundation for modern computing.
This map shows the decentralized node topology of ARPANET in the United States, juxtaposed against a seemingly blank technological void in the Soviet Union. For decades, the narrative in the West has focused on how the Soviets failed to build a decentralized internet, but that assumption falls apart when you look at the design itself. Soviet engineers were never trying to build a decentralized communication protocol. Their objective was distinct. They wanted to use computational power to automate and mathematically optimize a planned socialist economy. In the 1950s, the Soviet administrative apparatus was operating on a massive scale. Managing the production, distribution, and pricing of every good across a continent-spanning empire required an overwhelming volume of manual calculation. To solve this, Soviet computer scientists produced world-class hardware and sophisticated mathematical architectures. The national network they designed failed due to political self-preservation, not technical incompetence. The push for this computational network was spearheaded by two figures. The first was Anatoly Kitov. Coming from the military apparatus, Kitov realized that high-speed hardware processing was the essential requirement for managing vast logistical operations. The second was Viktor Glushkov.
Glushkov originated in pure theoretical mathematics, solving complex problems related to topological groups before turning his attention to the mechanics of computing. These two distinct disciplines, military logistics and pure mathematical theory, meshed. Together, they formed the vanguard of Soviet cybernetics, treating the entire national economy as a manageable, computable system. Their partnership reveals a central historical tension. These two minds pioneered the foundations of modern computer science, only to find that the very state they were trying to save refused to deploy their solutions. This diagram shows the architecture of Kitov's 1959 M100 computer. Achieving 100,000 operations per second, it used a mechanism called conveyor processing. Look at this data pathway. The machine begins processing the next instruction before the previous one finishes. In computer science, this hardware innovation is known as instruction pipelining, a standard feature in contemporary CPUs. Physical data entry was incredibly slow, relying on media like this standard punch card. Internal processing speed had to be exceptionally high to compensate. Beyond ballistic calculations, the Soviet state required massive processing power for the millions of daily equations required to plan economic production. Kitov's hardware pipelining provided the necessary physical engine. Without it, attempting to computationally manage an entire national economy would have been physically impossible. This illustrates the core concept from Viktor Glushkov's 1961 text, Synthesis of Digital Automata. By treating hardware as mathematical abstractions, computer components could be expressed as algebraic equations. This allowed engineers to algorithmically generate complex physical component layouts, formalized in his project system. This theoretical work laid the direct foundation for the computer-aided design, or CAD systems, that engineers rely on globally today to design microchips. Glushkov realized the physical limits of sequential processing, where computers execute one command at a time. To bypass this, he developed the macro conveyor. This diagram shows how that concept was implemented in the ES2701 computer. It utilizes a multiple instruction, multiple data, or MIMD architecture. Instead of a single stream, parallel command and data streams process simultaneously. In modern computing, MIMD architectures form the basis for multi-core processors and supercomputers. They allow different tasks to be executed across multiple processors simultaneously. Through abstract mathematics, Glushkov bypassed hardware limits, establishing parallel processing architectures that allowed computing power to scale. Managing the logistics of this landscape required an organizational architecture capable of processing data across 11 time zones. Kitov's 1959 Red Book planned a dual-use unified state network for military and civilian data, starting with local manufacturing nodes. By 1962, Glushkov evolved this into OGAS, where data lines flowed upward from these local nodes into 100 centralized regional broadband hubs. OGAS relied on macroeconomic models to collect real-time reporting data from over 20,000 distinct enterprise centers scattered across the Soviet bloc. At the local tier, environments like the Lviv television plant successfully implemented a localized automated management system that tracked parts, labor, and quotas. This localized data was then meant to stream up from the regional hubs and converge into a single apex node, state planning agencies like Gosplan, giving administrators the ability to mathematically model various economic outcomes. OGAS was a centralized hierarchical machine designed to execute an economy algorithmically, not a peer-to-peer internet for communication. But Kitov's Red Book proposal faced immediate political backlash under Nikita Khrushchev. The network project met its first major rejection from the state. The project's primary opposition came from within the Central Statistical Administration. The agency argued the network was too costly and technically complex to implement. The actual threat, however, was structural. Centralizing raw economic data through an automated computer network threatened the existing power dynamics of the mid-level bureaucracy. Algorithmic governance requires strict data transparency. Implementing OGAS would have stripped administrators of their ability to manually alter production reports, hide inefficiencies, or manipulate quotas. Officials systematically delayed the project. Under subsequent leadership, including Leonid Brezhnev, OGAS was endlessly trapped in committees and buried to preserve the bureaucratic status quo.
The Red Book and OGAS were technically viable engineering feats, but exact, undeniable data was politically lethal to the mid-century Soviet bureaucracy. The state's rigid centralization required high-level computational management for survival, yet the political structure rejected the transparency necessary to execute it. Measuring the success of Kitov and Glushkov against the survival of Western decentralized networks like ARPANET is a historical miscategorization. They were building distinct machines for distinct reasons. Their legacies survived in pure computer science. The mathematical synthesis of digital automata and the early development of MIMD parallel hardware are foundational to how we build computers today. Furthermore, the theoretical blueprints of OGAS directly anticipated modern enterprise architecture. Look at the OGAS structure again. The regional hubs are what we now call cloud computing. The macroscopic analysis is big data analytics, and the local node management is a distributed ERP system. These structural concepts remain highly relevant as governments globally push toward comprehensive e-government models, attempting to digitize and manage civil services at a massive scale. Kitov and Glushkov successfully theorized the architecture for digital economics. They simply did it decades before the physical hardware or the global political landscape was ready to accept the reality of algorithmic governance.
When we think about the Cold War origins of computing, the narrative usually starts with Western projects like ARPANET, the deployment of decentralized packet switching networks designed to survive a nuclear strike by distributing data across multiple independent nodes. Across the Iron Curtain, the Soviet Union faced the exact same geopolitical pressures. Yet, by the end of the Cold War, the USSR had no nationwide civilian computer network. There was no Soviet internet. It is tempting to attribute this blank space to an inability to manufacture hardware or a lag in computing research, but the historical record contradicts that assumption. Soviet computer scientists were producing rigorous, state-of-the-art research in digital automata, cybernetics, and network topology, frequently matching Western theoretical breakthroughs. Their central constraint was economic. In a centrally planned command economy, there are no market prices to naturally signal supply and demand. The state must manually calculate the allocation of millions of goods, labor hours, and resources across billions of variables. The failure to build the Soviet Internet provides a precise case study in a socio-technical paradox, a scenario where the technical architecture required to optimize a system poses a direct existential threat to the administrative bureaucracy running it. In 1954, Colonel Anatoly Kitov established Computing Center No. 1. At the time, Soviet military computing was strictly arithmetic, focused almost entirely on calculating satellite trajectories and missile ballistics. Kitov recognized that computer architecture could be applied differently. He argued that machines could pivot from pure math to non-arithmetic processing, specifically data retrieval and large-scale organizational management. By 1959, he formalized this concept in a proposal known as the Red Book Project. It outlined a total restructuring of the Soviet command economy based on cybernetic principles. The Red Book's core architecture relied on building a unified state network of computing centers. Kitov designed this as a dual-purpose network, a shared infrastructure capable of managing both the armed forces and the civilian economy simultaneously. Knowing mid-level bureaucrats would resist systemic overhaul, Kitov bypassed them entirely, sending the Red Book directly to the head of the Soviet state, Nikita Khrushchev. The political immune system reacted immediately. State leaders rejected the shared network outright. Kitov was expelled from the Communist Party and removed from his position at the Military Computing Center. Kitov's Red Book established the first rule of Soviet networking. Centralized political systems instinctively attack any infrastructure that attempts to automate or distribute their exclusive control over information. Following Kitov's dismissal, computer pioneer Viktor Glushkov took up the mantle of economic automation. Glushkov realized that before attempting to network the entire nation, scientists had to solve the physical processing limitations of computers themselves.
In his 1961 work, Synthesis of Digital Automata, Glushkov applied algebraic methods to mathematically abstract computer architecture, laying the theoretical groundwork for radical hardware redesigns. He targeted the von Neumann bottleneck, where a CPU processes instructions sequentially, limiting complex economic modeling. To bypass this, Glushkov proposed a macro-conveyor architecture. Classified today as a MIMD system, it replaces a single queue with multiple parallel channels, processing many data streams concurrently. This theoretical framework was physically realized years later in machines like the ES-2701 supercomputer, achieving a level of concurrent processing that pushed Soviet hardware past the boundary of 1 billion operations per second. Escaping the von Neumann bottleneck solved a distinct mathematical requirement: building a machine capable of ingesting and modeling the infinite variables of a national economy in real time. With the processing theory solidifying, Glushkov began developing a system authorized in 1962 by state leadership, OGAS, the State Automated Management Information System.
The operational goal of OGAS was highly specific. It aimed to continuously collect raw reporting data from national factories, centralize that data for processing through macroeconomic models, and output mathematically optimized production plans. The physical backbone would be a revived unified state network of computing centers. The topology required 100 large regional hubs connected by broadband channels. From those hubs, the network branched down, physically wiring 20,000 enterprise centers across the state. The intended data pipeline was bidirectional. Raw, unfiltered production metrics would flow continuously up the hierarchy to the hubs, while optimized economic directives would cascade back down to the factories. The OGAS blueprint was an exact digital mirror of the command economy it was built to run, mapping processing power directly over the state's physical geography. When the draft for OGAS was submitted in 1964, it hit a bureaucratic wall. It met severe resistance from powerful agencies, specifically the Central Statistical Administration and GAUS Plan. The economy operated on asymmetric information. Factory managers routinely hoarded data, hiding excess capacity and inefficiencies, so they could negotiate lower, easily achievable production quotas from the state. OGAS network threatened to bypass them entirely. By automating data collection at the factory floor, the network would stream pure, unmanipulated metrics directly to the central hubs. The Soviet bureaucracy realized that real-time data transparency would strip mid-level managers of their ability to control information. It would effectively eliminate their administrative leverage. Simultaneously, top-level leadership shifted. The new administration, led by Leonid Brezhnev, favored bureaucratic stability and the preservation of the existing power structure over technocratic reform. The state rejected OGAS. The mathematical models were sound, and the hardware was functional. But digitizing the command economy meant empowering a new class of technocrats, an act that would render the existing political apparatus obsolete. While the national macro network was never completed, the underlying computer science developed by Kitov and Glushkov succeeded in highly specific, domain-level applications. In 1967, Glushkov successfully launched an automated management information system at the Lviv television plant. It managed the factory's inventory and output autonomously. The Lviv system proved so effective that its core architecture became the standard enterprise resource planning model. It was eventually deployed across heavy industry sectors and 9 separate defense ministries. On the software side, Kitov led the development of ALGEM, an algorithmic programming language specifically built for economic and mathematical problem-solving, which was adopted by hundreds of enterprises across Eastern Europe. These localized, disconnected systems generated massive structural demand, ultimately creating a 700,000-person Soviet IT industry and laying the technical foundation for the modern Russian digital economy. The absence of a Soviet internet obscures what these scientists actually achieved. Kitov and Glushkov successfully automated the isolated industrial nodes of a superpower, even as the state forbade them from connecting the wires between them. The Soviet computing pioneers achieved a striking technical vindication. They proved that advanced MIMD architectures, advanced structural programming, and complex network topologies could be engineered under intense geopolitical isolation. Yet, their life's work remained deliberately fragmented and isolated, halted by the very same state bureaucracy that had originally commissioned it. The failure of OGAS remains a foundational case study for modern systems architects, offering insights that transcend its Cold War origins. No technical architecture,
regardless of its mathematical perfection or raw processing power, can ever be successfully deployed if its operational efficiency fundamentally contradicts the survival incentives of its host organization.
Modern histories often describe the Soviet Union's failure to build a nationwide computer network as an inevitable result of inferior computer science. This narrative suggests the state simply lacked the engineering capability to connect its territory. However, the aerospace achievements of the 1950s tell a different story. To calculate the orbital mechanics and telemetry required for the Sputnik 1 launch, the Soviet state relied on an immense and highly reliable computational infrastructure. At the center of this infrastructure were researchers like Anatoly Kitov and Viktor Glushkov, whose work in early computer science directly rivaled the progress being made at Western institutions like IBM and ARPA. The stalling of the Soviet digital network stemmed from a direct incompatibility between the transparent, horizontal routing of digital data and the rigid, vertical hierarchy of the Soviet bureaucracy. Distinguishing the mathematical achievements of these engineers from the political failures of their state provides a more accurate history of the birth of modern computing. In the 1950s, hardware engineers globally were hindered by the von Neumann bottleneck. Because CPUs processed data faster than they could access memory, processors spent significant cycles sitting idle while waiting for instructions. Anatoly Kitov addressed this delay through his work on the M100 architecture, a system designed to push Soviet hardware beyond these physical limitations. Kitov's primary innovation within the M100 was the conveyor processing system. This schematic shows the difference. Rather than waiting for an instruction to finish, the hardware begins the next one immediately. Overlapping these execution steps creates a massive increase in mathematical throughput, allowing the arithmetic device to stay active even as it retrieves new data. This pipeline methodology was officially patented in 1959, marking a proactive shift in Soviet structural engineering. These researchers independently solved foundational bottlenecks that still dictate microprocessor design today, demonstrating a high degree of technical autonomy from Western designs. Kitov realized the mathematical engines used for missile ballistics could also process non-arithmetic logic. This insight allowed computers to perform complex information retrieval and high-level administrative management. He developed associative programming and the algorithmic language AlGem to specifically handle the enormous datasets required to manage a national economy. In 1959, Kitov sent a formal proposal to Nikita Khrushchev's government. It was known as the Red Book. The proposal outlined the Unified State Network of Computing Centers, or USNCC. It was a radical design for a dual-purpose network that would serve military defense while managing the civilian economy. The USNCC was designed to utilize distributed computing hubs across the country, collecting and reallocating economic data in real time to optimize production. This network design presented a direct challenge to the status quo. It offered to move the state away from an administrative command style and toward a purely data-driven management model. While Kitov focused on the network, Viktor Glushkov sought to automate the physical design of computer architecture itself. In 1961, Glushkov published his theory on the synthesis of digital automata. He used mathematical abstraction to map internal computer structures. This allowed physical components to be generated through algebraic expressions, ensuring a level of precision that manual design could not match. This algebraic logic powered the Project CAD system, creating one of the first conceptual frameworks for computer-aided hardware design. Glushkov pushed to bypass standard hardware limits by theorizing an entirely different non-von-Neumann architecture. This is a visualization of the multiple command and data streams architecture, which Glushkov called the macro conveyor. This parallel approach allowed computational performance to scale almost infinitely, simply by adding more parallel hardware blocks to the system. The physical realization of this parallel processing theory was the ES-2701 supercomputer. Glushkov's algebraic abstractions provided the physical capability to execute the massive simultaneous calculations required for modeling a national economy. In 1962, Alexei Kosygin commissioned Glushkov to transition these hardware theories into a macroeconomic application. The project was named OGAS, the State Automated Management Information System. a digital framework designed to run the command economy. The base of the system relied on factory-level automated management information systems, which were first implemented at the Lviv television plant. The Lviv system automated mass production metrics, serving as a granular data intake point for the larger nationwide network. The proposed scaling topology for OGAS would connect 20,000 enterprise centers to a grid of 100 high-capacity regional hubs. The network utilized broadband communication channels, with active message switching to connect these distributed databanks. On top of this network, the Displan decision support system allowed planners to test macroeconomic models in real time. OGAS stood as a fully theorized, technically viable precursor to modern, cloud-based enterprise resource planning systems. The OGAS architecture relied on a specific operational requirement: immediate, horizontal data flow between regional hubs. This horizontal logic was incompatible with the Soviet state's rigid, vertical information hierarchy. Immediate bureaucratic resistance formed within the Central Statistical Administration and Gosplan, where officials questioned the project's cost and complexity. The transparent digital network posed a direct political threat to the middle managers who maintained power by manually controlling and often manipulating production data. The systemic efficiency of automated digital routing stripped the ruling bureaucracy of its discretionary power. The OGAS network faced rejection because it would have worked exactly as intended, rendering the existing power structure obsolete. The state's refusal to adopt a digital nervous system left its planned economy blind to its own inefficiencies, contributing to its eventual collapse. The rejection of the hardware networks did not erase the foundational mathematics generated by Kitov and Glushkov. Their frameworks in algebraic algorithmic languages and medical informatics survived the state, continuing to influence research decades later. Today, the global history of computer science records these pioneers as foundational architects, moving past the narrative of technological failure. The history of Soviet computing proves that brilliant computer science can be engineered in isolation, but the deployment of macro-scale networks is a choice made by the socio-political system hosting them. The prevailing historical narrative suggests that Soviet computer science failed because it never produced a decentralized, organic communication network similar to the Internet. But engineers in Moscow and Kyiv weren't attempting to build a public peer-to-peer web. Their objective was the total automation of the state, architecting a centralized digital command economy to run every factory and farm in the Soviet Union. This split represents a structural divide. While Western pioneers were exploring organic node and edge webs, the Soviets were focused on a rigid three-tier command hierarchy. Judging Soviet computing by the standards of the modern Internet ignores what they actually achieved: the successful blueprinting of a massive, national-scale e-government apparatus. This movement began with Anatoly Kitov. A colonel in the Red Army, Kitov realized that digital computers could process economic data faster and more accurately than the thousands of human bureaucrats currently managing the state. Kitov found his inspiration in the secret libraries of the military. In 1951, he read Norbert Wiener's Cybernetics and recognized that the same mathematical principles used to stabilize machines could be applied to stabilize an entire economy. Kitov soon partnered with Viktor Glushkov, a brilliant mathematician who had already solved one of Hilbert's famous problems. Glushkov took over the Institute of Cybernetics, turning it into the primary center for Soviet computer research. Together, they shared a specific ambition: moving computer usage away from isolated military ballistics toward total macroeconomic management. Kitov and Glushkov shifted the focus of Soviet computer science, treating the machine not as a giant calculator for physics, but as a systemic engine for managing the state. In 1962, the Soviet leadership approved the OGAS project. Alexei Kosygin officially ordered the creation of a unified state network to modernize the command economy. The blueprint for this network, known as EGSVTS, utilized a strict hierarchy. A massive command center in Moscow sat at the apex. Below the capital, 100 regional centers in major industrial cities would aggregate local data and transmit it directly to Moscow. At the base, 20,000 individual nodes represented every factory and organization in the country, creating a direct digital feed to the higher centers. To manage this volume, the network used message switching over broadband channels. Data pulses moved exclusively upward, concentrating local output into a single national picture.
At the factory level, this was managed by the Lviv system. This was the first standardized automated management information system designed for mass production. This system used algorithms to manage local supply chains and assembly lines, generating the precise, real-time data required by the national network above it. Collectively, OGAS functioned as a nation-scale enterprise resource planning system, conceptualized decades before the private sector equivalents. However, the architects faced a major engineering bottleneck. Building custom hardware fast enough to manage a nation of 250 million people was impossible through manual design. Glushkov solved this in 1961 with his theory on the synthesis of digital automata. At the time, designing a computer meant drafting physical circuits like these, wire by wire and gate by gate. Glushkov's theory allowed engineers to translate these physical components into algebraic expressions. Once a machine was defined by math, its architecture could be manipulated logically.
This abstraction enabled the project system, where one computer used these algebraic models to automatically generate the blueprints for another computer's hardware. By proving hardware design could be performed by a machine through pure logic, Glushkov established the framework necessary for all subsequent computer-aided design systems. Even with automated design, traditional computer architecture struggled to process the simultaneous economic inputs of thousands of factories at once. Most computers follow the von Neumann architecture, which funnels a single instruction and a single data stream through one pipeline. Processing massive real-time economic data through this single channel created a fatal backup. Glushkov responded with a patented solution, macro-conveyor architecture, known today as MIMD processing. In a multiple instruction, multiple data system, the processor splits into parallel tracks. This allows the machine to handle massive volumes of simultaneous inputs without choking at a central node. Using this architecture, the Soviet ES-2701 and EU-1766 supercomputers broke the barrier of 1 billion operations per second. The demands of the command economy forced Soviet scientists to innovate beyond traditional computing and develop the parallel processing paradigm still used in supercomputing today. On a technical level, the OGAS macro network was a sophisticated, mathematically sound blueprint for a digital state, but the project was stopped by a human firewall, the Soviet administrative bureaucracy and the Central Statistical Administration. Algorithmic economic reporting required total data transparency. This was a direct threat to mid-level managers who maintained their power by manipulating production figures and hiding inefficiencies from the central leadership. To protect their political positions, bureaucrats stalled funding and dismantled the network's integration. They effectively blocked the data streams with administrative red tape. The project died to preserve the status quo of the Soviet leadership, not because the technology failed. Decades later, the topology of the OGAS project has reappeared in the private sector. Modern corporate cloud architectures and global supply chain networks use the same hierarchical logic Kitov and Glushkov pioneered in the 1960s. The absence of a Soviet internet reveals a core principle of systems engineering. Computational architecture, no matter how rigorous, is ultimately subordinate to the socio-political operating system it inhabits.
The history of modern computing is usually told with a strict geographic bias. This timeline maps the standard milestones of global networking. You see ARPANET coming online in the United States in 1969 and Cyclades activating in France by 1972. In this prevailing narrative, Soviet computing during the Cold War is categorized as entirely derivative, relying on stolen Western designs or lagging decades behind. Historians often use a specific label to summarize this technological dead end, the Internet. Primary archival research reveals a different reality. The Soviet Union was producing highly advanced theoretical computer science. Researchers were independently achieving major breakthroughs in algebraic automata and proposing macro-conveyor architectures long before similar concepts were adopted in the West. The absence of a Soviet internet occurred despite this scientific progress, halted instead by the internal friction of the state. To understand this, we have to look at the environment where Soviet computational research began. Anatoly Kitov initiated this work to solve complex ballistics and rocketry problems for the military. Viktor Glushkov took this mathematical foundation and shifted the focus toward civilian economic applications. In 1959, Kitov proposed the Red Book project, a massive, dual-purpose national computer network designed to manage both the armed forces and the state economy. By 1962, Glushkov evolved this concept into a comprehensive blueprint known as OGAS. OGAS envisioned an administrative infrastructure for the entire nation. This topology shows 100 regional hubs, branching to connect 20,000 enterprise centers. Notice the timeline. This nationwide network blueprint was mapped out in 1962, 7 years before ARPANET. The engineers designed a cohesive digital topology, but a high-speed data network was structurally incompatible with the analog hierarchy of the Soviet state. In the early 1950s, the Soviet government viewed extreme suspicion. State ideologists officially banned the study of cybernetics, labeling it a capitalist pseudoscience designed to exploit workers. Kitov directly challenged this ban, demonstrating that cybernetics and mathematical modeling were operational requirements for a modern military and state economy. This rehabilitation of the science paved the way for Glushkov to publish his 1961 monograph, Synthesis of Digital Automata. The text introduced a novel concept. It demonstrated how you could mathematically represent physical computer hardware using algebraic expressions. By treating the components of a machine as mathematical abstractions, engineers could design complex computer systems algorithmically before ever building the physical hardware. This algebraic approach served as a direct early precursor to computer-aided design systems used by hardware manufacturers today. At the foundational level, Soviet hardware theory was mathematically rigorous, completely independent, and competitive with the best research in the world. The next step was proving these mathematical theories could survive contact with the Soviet planned economy. Managing mass production was difficult. Central planners attempted to set quotas and track complex industrial machinery using manual calculations and paper ledgers. To solve this, Glushkov's team deployed the Lviv ANMIS, an automated management information system, at a television plant in 1967. AMIS functioned as an early, highly effective form of enterprise resource planning. Here is the localized data loop. Raw materials and production metrics streamed continuously from factory machinery into a central mainframe.
The mainframe processed this data and instantly returned optimized scheduling pathways back to the factory floor, adjusting machinery in real time. AMIS provided operational proof that cybernetic networks could successfully micromanage state enterprises. Glushkov's ultimate ambition was to take the localized success of AMIS and scale it up to manage the entire macroeconomic output of the Soviet Union. Doing so presented an immediate technical roadblock. Standard von Neumann computer architectures process commands sequentially, which creates a data bottleneck when trying to route information for an entire nation. Glushkov bypassed this limit by designing early macro conveyor architectures, known today as MIMD, or multiple instruction, multiple data systems. This visualization compares the two approaches.
Instead of a single file line of data choking at a processor bottleneck, MIMD architectures allow multiple streams of commands and data to be processed simultaneously, acting like a multi-lane highway. To deploy this processing power, the state would construct the unified state network of computing centers, providing the physical infrastructure for OGAS. The system was engineered to collect, route, and analyze economic data across thousands of interconnected nodes at speeds and volumes previously thought impossible. OGAS was engineered to be a real-time, automated operating system for a global superpower. But a technical blueprint rarely survives a messy political reality. The strongest opposition to OGAS came from the Central Statistical Administration and Gosplan, the very agencies responsible for economic planning. Soviet reporting relied entirely on an analog chain of command. Factory managers routinely altered paper quotas and manipulated production numbers to meet rigid state demands. An automated, real-time data network eliminated that friction. Direct data streams bypassed mid-level managers completely, stripping bureaucrats of their ability to massage the numbers. Top political leadership failed to grasp technocratic adaptation. They viewed an automated, transparent network as a threat to the Politburo's absolute control over information. To kill the project, the Statistical Administration insisted the network was far too expensive and overly complex to implement. The Soviet administration actively suffocated the network to preserve its own analog existence. They chose the illusion of control over actual efficiency. Without support from the Central Committee, the OGAS macro network was permanently shelved in the 1970s.
While the national network died, the localized nodes survived. The AMOS architecture became the gold standard for managing Soviet defense industries. The hardware designs and programming languages, like Algem, proliferated across the Eastern Bloc and were integrated into hundreds of enterprises. Glushkov continued his research, culminating in his 1982 visionary concept of paperless informatics, outlining a fully digitized society. Today, those early frameworks directly inform the architecture of the modern Russian digital economy and its e-government platforms. The primary research proved its validity by outliving the political collapse of the state that originally funded it. The careers of Kitov and Glushkov end in a specific type of tragedy: brilliant engineers who solved the math but were defeated by the bureaucracy. Ultimately, their pioneering work leaves behind a powerful, enduring lesson regarding the complex intersection of systems engineering and human society. You can design a cohesive digital architecture, but it will fail if it threatens the socio-political structure it is meant to serve. This hand-drawn diagram maps the early nodes of ARPANET. It represents the standard historical narrative of Cold War computing. The United States successfully engineered a decentralized communications network that birthed the Internet, while the Soviet Union stagnated. That comparison assumes the two superpowers were trying to solve the same problem. The United States wanted a survivable, distributed communications web. The Soviet Union had an entirely different objective. Computer scientists Anatoly Kitov and Viktor Glushkov were not trying to build an open web. They were engineering a highly structured national-scale computing model specifically designed to run a centrally planned economy. Evaluating Soviet computer science by looking for a decentralized internet obscures the actual engineering they accomplished. They engineered an entirely different approach to systemic logic. A free market economy relies on decentralized pricing to allocate resources. A centrally planned state requires a strict, hierarchical flow of data from the bottom up. Managing the entire Soviet macroeconomy meant processing an immense volume of physical information. The state had to track millions of production quotas, inventory logs, and supply chain inputs every single day. Automating that process required absolute data transparency, and absolute data transparency is exactly what the existing Soviet bureaucratic apparatus feared most. The eventual collapse of a national Soviet network stemmed from a socio-political collision rather than a deficit in hardware or mathematics. The history of Soviet cybernetics is a tragedy of systems engineering. A mathematically sound architecture was destroyed by the state organization it was designed to save. In 1959, Anatoly Kitov drafted a proposal that became known as the Red Book. Kitov had spent the decade running military ballistics on early Soviet supercomputers like the Strela and the M100, and he recognized the broader potential of mass computation. He proposed the Unified State Network of Computing Centers. The design called for a dual-use grid spanning the USSR. By processing military defense calculations and civilian economic planning data concurrently on the same pathways, the state could maximize hardware efficiency and eliminate redundant systems. The proposal met with total rejection from the Soviet leadership. Kitov was stripped of his position at the Ministry of Defense's Computing Center and expelled from the Communist Party. Kitov's system required moving from an administrative command style of leadership to a strict, data-driven model. The proposal was killed because it stripped power away from party officials who relied on manually dictating economic outcomes. Following Kitov's dismissal, Viktor Glushkov realized that before a national network could be built, the fundamental architecture of the computers themselves had to be mathematically restructured. In his 1961 work, Synthesis of Digital Automata, Glushkov proved physical machine structures could be optimized using algebraic abstraction. This allowed the Kiev Institute to move beyond standard von Neumann models, developing what Glushkov called macro-conveyor architectures, an early form of parallel processing. Glushkov tested this computational theory in the real world. In 1967, his team deployed the Lviv system at an enterprise television plant, creating an automated management information system for a facility with a mass character of production. The Lviv system succeeded.
It proved that Glushkov's abstract mathematical theories could effectively track and optimize complex industrial output on a factory floor. With the mathematical foundation proven at the factory level, Glushkov attempted to scale the system to the entire national economy through a project called OGAS. The base layer of OGAS was massive data collection. It required standardizing reporting metrics and gathering physical inventory data directly from 20,000 local enterprise centers. That raw production data would then be funneled upward into approximately 100 processing hubs located in major industrial cities. Finally, utilizing broadband communication channels, it would be fed directly into a central hub in Moscow. An architecture that perfectly maps an economy in real time removes the need for manual intervention in supply chains. It replaces bureaucratic intuition and guesswork with exact mathematical certainty. That certainty directly threatened the primary gatekeepers of the Soviet economy, particularly the Central Statistical Administration and the Central Planning Agency Gosplan. A continuous flow of automated, unalterable data bypassed the traditional silos of power that these agencies relied on to govern. The agencies retaliated by demagogically citing high hardware costs and technical complexity, successfully stalling the OGAS project in endless committee reviews. At the highest levels, party leaders feared that automating the state meant handing their power over to technocrats and computers. OGAS was intentionally killed. The political apparatus required the ability to manipulate economic data to maintain its control. A transparent, mathematically rigorous system threatened the primary function of that bureaucracy. Though the national macroeconomic network was blocked, the underlying science survived. The Soviet IT industry successfully grew to employ over 700,000 people. Kitov and Glushkov deployed automated management systems like the Kuntsevo system strictly within the military sector, eventually expanding it across 9 defense ministries. Their hardware engineering advanced in isolation, leading to machines like the ES-2701, a macro-conveyor supercomputer capable of executing over 1 billion operations per second. Confining these advanced systems strictly to the defense sector kept the military highly competitive, but it guaranteed that the civilian planned economy would eventually stagnate and collapse. The research produced by Kitov and Glushkov did not disappear with the Soviet Union. Their foundational work underpins modern Russia's digital economy national projects today. Evaluating historical computing solely by the creation of a distributed internet erases the reality of alternative, highly advanced models of machine logic. The history of Soviet computing serves as a historical lesson on the inherent friction between brilliant systems engineering and state power.